Yes. So we talk about CMB maps, and we say that so basically what we measure is the fluctuations. Okay. So, so I showed you a CMB map with like hot and cold spots, right? And I told you that this from the power spectrum we can estimate the cosmological parameters. So what we can measure like total at any direction, theta and phi. We can measure the total. Okay. So the mean temperature of that, if I calculate average over all theta and phi, okay. So the mean temperature is 2.725 Kelvin. And the fluctuation, what I told you last time, at any given direction is order of tens of microkelvin. Okay. So this any direction, the temperature, we can write it as a mean temperature, which is 2.725 Kelvin plus minus this fluctuation. Okay. So it can be higher, slightly higher than 2.725 Kelvin or slightly lower than 2.75 Kelvin. And this fluctuation delta T over T is order of 10 to the power minus 5. Okay, so we can take this fluctuation map delta T theta, and what we are interested to compute is the power spectrum, okay, which is C. So let me go through the steps. So this delta T theta phi, we write it in terms of ALM, YLM, theta, and phi. Okay. So here there are two variables, theta and phi. Okay. So this is in, we call it as real space. Okay. And when doing the Fourier transform, there are actually two sums. One is over L, which is 0 to infinity, and M, which is minus L to plus L. Okay. So we are just converting this basis to L and M basis, which is harmonic space. So it's easy to, because ultimately we are not interested to study the maps, because the maps are just fluctuation maps. So what we are interested is the RMS power, or like how, at what scale the power is maximum or less. And based on that, we can derive the cosmological parameter. So the cosmological parameter depends on the power spectrum. And the map is just one realization of the power spectrum. So basically we transform this real space to harmonic space, and we define CL. So this is like true definition of power spectrum, which is defined as ALM star average over all. So this is ensemble average. So this is average over all the possible skies. So basically, if we can go to different galaxy and measure the CMB from there, so we can collect as many as sky as possible, and then we can take an average. So that is what ensemble average means. But we don't have option to go anywhere. So what we measure only one sky. So we can define an estimator. So estimator means we cannot do this this step. So what we can do is given ALMs, whatever we get it from the Fourier transform, we can construct a CL from that, which is defined as 1 by 12 plus 1 ALM star. Okay. So now, if I want to see if this estimator is biased or not, whether it gives me the correct value or not. So in principle, if I apply this estimator and average over many realization, what I will get is 1 by 12 plus 1 sum over ALM star. Okay, average over. So this ensemble average applies to both sides. This gives me CL true value. So this CL, we can take it out of this summation sign. And then we have, so this sum is from minus L to plus L. Okay. So then we have 1 by 12 plus 1. And then sum is from minus L to plus L. And there will be 1. Okay. So if you are just summing over M from minus L to plus L, so this gives me basically 12 plus 1. And this 12 plus 1 and this 12 plus 1 will cancel. So on average, there is no bias on this estimator. Okay, but it is just one realization of the true spectrum. So when we say lambda CDM model, okay, so this model is, we say, is a true spectrum. So what we measure is, say, L into L plus 1 CL by 2 pi. So suppose we get some data points, okay, with some error bars. So it's not necessary. So what we measure is just one realization of the sky. Okay, so this is sky estimated through this estimator. So suppose we have a full sky map of CMB. And what we are interested to know is the true model. Okay. So the true model is not necessary that it goes through all the points. It can be, there will be fluctuation around that model curve. So what we observe is just one realization of that model. Okay. So now these ALMs have some properties. So this ALM, so this is, like I said, ALM is a complex quantity. So that's why we take complex conjugate, multiply, and compute the CL. So if I take ALM star minus M, so this is same as minus 1 to the power M ALM. Okay. So, so this is one property that, so this, all the M's are not strictly independent. So if I know for a given L, so say L is equal to 2, okay, so M varies from minus 2, minus 1, 0, 1, 2, minus L to plus L. Okay. So if I know A 2, 0 or 2, say 2, 2, I know how it is connected with 2 minus 2, okay, through this simple relation. So this actually comes from the property of the spherical harmonics. So, so we need this YLM. So we can write it like this, or we can write it YML theta phi. Okay. So this is, so this L corresponding to whether it is monopole, quadrupole. So L is equal to 0 means monopole, which means just the average of the map. Okay. So since we are removing the average, so on the mean should be close to 0. So that's why we never look at monopole and dipole term. So dipole, I told you that it is coming from the motion of us with respect to the solar system. So we are always considering L greater than 2. So this is L equal to 2 is called quadrupole. Okay. And then L is equal to 3 is octapole. And like that it goes on. So this, so using this simple expression, CL tilde 1 by 12 plus 1 sum over ALM star, we can get the power spectrum. Now we can, suppose we are interested to calculate the variance or the error bar on the CL. So we can calculate variance of CL tilde. Okay, so there's a standard definition. You all know that. So CL tilde square, you average over realization minus CL average square. Okay. So that means, so if I do like many realizations, I will get what is the variance of the CL. Okay. So now I know how the CLs are defined. Okay. So we can generalize this expression and we can write it that sum over A L1 M1 A L2 M2 star is same as 2L plus 1 CL delta L1 L2 delta M1 M2. Okay. So only if it is same, whether when it is L1 is equal to L2 or M1 is equal to M2, we get the CL. For other cross terms, it is 0. Okay. Yes. So this thing, so we can start with the general definition and then we can put this constraint that if it is not equal, M1 not equal to M2 or L1 not equal to L2, we get 0 contribution. So this is L1 plus 1, then we can have L2 plus 1, sum over. So there are two sums, M1, M2. Then we have A L1, M1, A L1, M1 star, A L2, L2, M2, and A L2, M2 star. Okay. So this is a square term. And then we are taking an ensemble average of that. And minus, here it is basically, we get a true CL. Right? And this is a square term, so this is L1, L2. So this, we can use Wick's theorem and write this product of 4. So it's like a 4-point correlation function. We can write in terms of 2-point correlation function. So any, for a Gaussian distribution, so you know that the skewness is 0. The kurtosis you can write in terms of 2-point correlation function. So any even order of correlation function you can always express in terms of 2-point correlation function. Okay. So there will be 3 combinations. So one is between these two and this two. Okay. So this is 1 by 2L plus 1, 2L2 plus 1. Okay. So sum over M1, M2. So this one gives you CL1 and CL2. Okay. Yes. And then you can combine this one and the complex conjugate of the other and this two. You will get delta L1, L2, delta M1, M2. So if you if it is L1 and L2 are not same, they will cancel. So only in the case where these are same, so they will contribute. So in the variance, so effectively this term becomes 1. Otherwise, there will be no CL. So we get basically 3 contribution, and the other ones are you combine this with this third term and the second and the fourth term using this property that ALM star, we can write it in this form. So then we will have another term which is minus 1 to the power M1 plus M2 CL1 CL2 delta L1 L2 delta M1 minus M2. Okay. So this so basically we will get 3 times CL1 L2, and there is 1 CL1 L2 we have to subtract. So at the end, what we will get is 2 by 2 L1. So all L1 and L2 are same. So we will get 2L plus 1 times CL. Okay. So it means that the variance, or like if I interested in the sigma, which is square root of the variance of the CL estimator. So analytically, we can compute for the full sky. So the error bar depends on the CL. Okay, so it is proportional to CL. Only there is a reduction factor, which is 2L plus 1. So when we go to high L values, so this decreases. At low L values, where suppose L equal to 2, so it does not decrease much. So that's why we have bigger error bars. So now, so we know, so basically this is simple mathematics, which tells you how to go from map to power spectrum. Now, there is complexity for the real data.
Excuse me, sir.
Yes.
Sir, in the deriving the standard variance of the CL, you've written 2 by 2L plus 1 into CL. And
Yes.
while you have taken the square root, you have taken outside of it.
No, there are 2 CL, so it should be CL square. Sorry.
Okay, sir.
Yeah, thanks. So then, so this is true if you have one map. Okay. So, but for the real sky, okay. So I told you there are what we have is the CMB, okay, which is the background radiation. Then we have foreground emission from different sources. Okay. So this is mostly coming from synchrotron emission, free emission. I was talking yesterday about CIB, cosmic infrared background anisotropies. Then there is a Sunyaev-Zel'dovich effect. So there is a thermal Sunyaev-Zel'dovich effect. There is a kinetic Sunyaev-Zel'dovich effect. Then there are CO line emission. There is dust emission. Then there is a spinning dust emission. So I'm listing all of them now here. Emission. There is HCN line emission at 100 gigahertz. So these are the different molecular line emissions. Then we have point sources, which are infrared sources. So they are dust dominated. Okay. So they are like, yeah, so they mostly emit in the infrared frequencies. Then there are sources which are radio point sources. So there are different kind of sources. So some sources emit in the radio frequency, and some sources emits in the infrared frequency. So we will go into details in the last lectures where we see what we learn about those different kind of emission from the CMB observations. Then we have zodiacal light emission. So these are interplanetary dust. They also contribute in these frequency bands. Okay. So these are all clubbed together into foreground emission. And then we have instrumental noise. Okay. So this noise can be statistical noise. Okay. So it's like a white noise. We know the power spectrum. And if you integrate over a longer time, it will decrease. And then we have systematic noise. So this is something which is, suppose the instrument itself produce some noise within a systematic way, and it does not, when you average over it, it does not cancel out. So we have like 2 detectors. So ideally, if these the noise should be uncorrelated between these 2 detectors. So when we cross correlate, we can get rid of the noise, but it can be possible that these 2 they have a same family of horn antennas, so they can have same kind of systematic noise. So when you cross correlate, they don't decrease. Okay, so the idea is that so we for CL estimator, okay, so we are doing this 2L plus 1. ALM. So basically we are doing ALM square. We have one map, we can square it. Okay. So like I told you yesterday, there is this TT power spectrum, TE power spectrum, EE power spectrum. So what we have is you measure Stokes Q and Q and U Stokes parameter. So we can is used for intensity. For CMB reference, we can convert this to temperature. So this is because we always express in microkelvin, the fluctuation level. In principle, we can express them in intensity units, which is megajansky per steradian. So it's just a convention. So I is converted. So I is usually represented in megajansky per steradian. We convert into thermal temperature units. Okay. So that is why CCL fluctuation, but is units of temperature. And this Stokes Q and U, we can convert into divergence free component and curl free component. Okay, so that is E and B. So then we can generalize this formula and say that we estimate, say, TT power spectrum. So then what we do is we do ALM of T and ALM of T. So we have delta T map, we decompose into ALM, okay, and we get this ALM. We just, so basically it's a star complex conjugate. We get another ALM from the same map, and we just, so it's basically square of that. Now we have this E map. Okay. So we can do same decomposition. We can get E YLM and similarly B, which is ALM B YLM. Okay. So then we can define CL tilde TE, which is 1 by 2 L plus 1 ALM T ALM star E. Okay. So it's possible to multiply, not necessarily always same ALM. We can multiply from two ALM generated from the two maps. So then we can get a cross power spectrum. Okay. So this is like a variance. Okay. This is like a covariance. Or usually we call it as cross power spectrum. Cross power spectrum. And this is called as auto power spectrum. Okay. And we can similarly, so basically we have three, so I'm not going to write it. So we have T, E, and B. So we can think about all the possible permutation combination. So it will get TT, TE, TB, EE, EB, and BB. Okay. So usually, so with Planck, we measure, so Planck measures TT, TE, and EE. Okay. So the BB is the limit of the noise for the Planck, but there are other experiment like BICEP or SPT or ACT. So they target to measure this BB power spectrum. And from parity violation argument for CMB, TEB and TB should be 0. Okay. So if we find some deviation from EB and TB, it can highlight there is a parity violation. Okay. So it can have this auto power spectrum. So in principle for CMB, we can have only this 4, TT, TE, EE, and BB. Okay. The others are generally used to calibrate the instrument. So they say maybe there are systematics in the data which can artificially produce non-zero EB. Okay, so from CMB we know that we know that it cannot have EB. Okay, so if there are non-zero EB, so it can rise from instrumental systematics. Okay. So what happens is that, so we, when we measure something, so to zeroth order, we have signal, which is CMB, and noise. Okay. So what we can do is whatever ALM decomposition we do for the map, it is ALM signal plus ALM noise. Okay. Now, if I square this thing, like the standard definition, 12 plus 1 ALM square. Okay. So then what I do is, so it is basically ALM signal square plus ALM noise square plus 2 ALM signal plus ALM noise. Okay. So ALM signal square gives me CL of the signal. ALM noise square gives me ALM CL of the noise. And then we have cross term. So usually signal and noise are uncorrelated. So there will be no cross term. So this, if I compute the auto power spectrum, I will get contribution of the signal plus noise. So this is not ideal case because we want to get interested in the signal. We want to get rid of this noise contribution. So what we can do is, we suppose for Planck, we measure like every 1 year or every 6 months we cover the sky. Okay. So in a 1 year, we can make 2 full sky maps. Okay. So we can say odd survey. So say 0 to 6 months. Okay. So we get ALM signal. So signal will remain signal. It will not change. And the noise, we get N1. So you get some noise in that period. And if you get another set of map from 7 months to 12 months, we get ALM signal plus ALM noise 2. Okay. So here the noise are uncorrelated. So in this case, when I multiply these two maps, so there will be ALM signal plus times ALM signal, so it will be square. But the noise, which is uncorrelated, so ALM noise 1 and noise 2 will cancel out. So in that case, if I do CL estimator like this, define 12 plus 1 ALM odd times ALM even. Okay. I can interchange these two quantities. I will get signal. Okay. So that's why the noise we can always cancel if it's statistical noise. If the noise are correlated in this two data set, then it will not cancel, and then we have contribution to those. Okay. So in the true sky, when we measure true sky, the real sky, so there is another complication, which is the beam. So it is not at RB, when we're looking at some theta phi direction. So it's not a pencil beam. Okay. So in that exactly at theta phi, we can measure it. So the instrument has some beam. Okay. So when we're looking at that direction, it has contribution from other points. So this delta t theta phi, we can write it as convolution with the beam function, which is, let me write it like this. And so n pointing, n represents my theta and phi. Okay. So it will have contribution from other direction and delta t n prime and dt omega. So it will be just convolve with the beam. So whatever the beam is, it can basically takes the average of nearby pixels with that beam response function, and the integrated effect we see at that point. So when we do this in terms of ALMs, okay, so it's convenient to write in terms of ALMs. So this ALM of the any frequency map, okay, we can write it as ALM CMB plus ALM foreground plus ALM noise. Okay, so a simple example. So previously I considered only signal plus noise. Here I'm considering So C is for CMB. Okay. So you can just write C or CMB. F is for foreground and N is for noise. Okay. But because of this beam effect, this two quantities get multiplied by BL. Okay. So this BL is the Fourier transform of this this beam function. So there is a real part of the beam, and BL is the like the power spectrum or of the beam. So this is something we keep in mind, and the CMB is frequency independent. So if there is a frequency dependence, it is coming from the foreground and the noise. Okay, so the noise will not get multiplied by the beam. So this is for, so when I write this, so this includes CMB and foreground, and the noise will be separate. Okay, so that is because noise is produced by the instrument. Okay, so that is basically the framework with which we work. So it's good to have this clear so that then you can like get your desired results. So you can add foreground noise, beam, and we can get like whatever we want. So for our purpose, we will use a software called Hillpeaks. Okay. So that is used for CMB data analysis. So if you want to work with map or to visualize the maps or compute the power spectrum, we can use this software. And it has a Python version of that code. So initially it was written in C and Fortran. So the Python version is called as HillPy. Okay. So this is basically Python version of Hillpix. So we need few things to understand like how they make the projection of the map, okay, which is important for our understanding. So basically the idea is that we have a full sky map with theta and phi. So theta is my latitude, okay, galactic latitude. So it goes from minus 90 to plus 90. Okay. So this is basically theta angle. It goes from south hemisphere to northern hemisphere. And then we have phi, which is galactic longitude. Okay. So it goes from 0 to 360. So in Hillpix, they don't use galactic latitude. They use galactic co-latitude. So it goes from 0 to 180. Okay. So they start from top. So this is 0. So you can always define whether you want to use latitude or longitude. So they choose pole latitude as northern galactic pole, and then they go from 0 to 180. It's just a convention. Okay. Now, in Hillpix or Hillpy, what they do is they divide the whole sky. They divide into number of pixels with equal area. So each pixel will have equal area. Okay. So it's not a rectangle or square things. So they divide according to the area or the like area occupied by the pixel. Okay. So they have some number which is called n side. Okay. So it has to be 2 to the power n. Okay. So you cannot choose any arbitrary n side. And this n side is related to the number of pixels by the relation, which is 12 times n side square. Okay. So once you choose what is the n side, so you can choose n side as 2, 4, 8. So you put n is equal to 1, 2, 3 like that. 16, 32, okay, like that. And depending on that, you can get what is, how many pixels are there. So like 2, if you put it, like 2 square is 4. So in that case, there will be 48 number of pixels. And similarly, you can, so it goes as square. So accordingly, you can, so in n side, it is factor of 2. In pixel, it is factor of 4. So each n side, if you increase, your number of pixel will increase by factor of 4. So basically, what is happening is that, so they choose a bigger pixel like that. Okay, so this is a n side 2. When they go to the next n side, so n side 4, so you divide this into 4. Okay. So then you go from 1 pixel to 4 pixels. So this is a pixel center. Now the new pixel centers are this 4 pixels. And then similarly, you can divide this each one into 4. Okay. So for the next higher order thing, you get 16 pixels. So this is how Hilpix works. Okay. So now we can calculate what is the area occupied by each pixel. So the total area of the sky is 4 pi. Okay. And the number of pixels is n pix. Okay, which is defined as 12 into n side square. So we know how much area each pixel will occupy for a given n side. And assuming it is this shape, then we can get what is the, like each side, how much is the like extension of the pixel. So theta pix, which is square root of this. So square root of 4 pi by n pix. So what it does is it divides the sky into number of pixels, like 0, 1, 2, dot, 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 n pix. And each pixel, it assigns some value. Okay, so maybe 3. So this is, I'm talking about delta t theta phi. Okay, so say 3, 2, 5, some arbitrary pixel number in say micro Kelvin units. So we don't keep the information about the pixel number. So it will give me an array, the data sets is like a column vector. Okay. And it gives some value, say 10 microkelvin, 20 microkelvin, like that. So we have to identify that the first number is the first pixel. Second number is the second pixel. Okay. And this first pixel corresponding to some theta and phi. And once we know what is theta and phi, we can just project it and show the map. But in Hilpix, there are two conventions which the people follow. One is the ring format, and another is the nested format. Okay. So both has some advantages. So that's why these two formats are defined. So in ring format, what happens is that, so you have the sky like that. So you start from the North Pole. Okay. So you assign that as like the first pixel, and then you go in round. Okay, and go down to the south. Okay, so last pixel will be the south pole. So the advantage is that, so if it arrange this one column vector arranged like that, so if I know what is the first pixel and the last pixel, which is the n pix, I can just looking at the values, I can say, okay, so this first pixel is probably in the North Pole. The last pixel is in the South Pole. The middle one is somewhere in the galactic equator. And accordingly, if I know how many pixels are there in between, I can tell, okay, so any number, it is where most probably it will lie. Okay, there are tools to do that, but it is at least to first order, I can tell that. So that is the ring format. All the Planck maps are in nested format. So nested format is basically suppose for some data analysis, you want to find what are the nearby pixels. Okay, so given this pixel, I want to find, so suppose for beam convolution, I want to find what are the nearby pixels so that I can apply the beam smoothing. So I want to know what is the pixel number of that. So here the problem is that when it goes from one end to another, so the pixel number can, it is continuous, but it's not guaranteed that the nearest pixel is the next ID. Okay, so it can go from this end and the next ID will be maybe here. Okay, and then it will continue like that up to this point, and then the next ID will be somewhere here. Okay, so there is a discontinuity. So to avoid that, there is a nested format, which is always find pixels, like start from 1, 2, 3, 4, 5, 6, 7, 8, 9, and then around 2, it will try to find 10, 11, 12. Okay. So around 13, it is like that. It will allocate the pixels so that all the pixels are close by. So they don't be very like pole apart. So that is the nested format. So usually this information is there in the header file. Okay. So you can always look at whether it is a ring format or nested format, and accordingly you can make the plot, because it just have the pixel number, so it does not say theta and phi. So this information is important, whether it is ring or nested. So most the original maps are in nested formats, but for our purpose, we will work with the ring format. Okay. Okay. So this is a basic definition of hill peaks. So let me give you a problem which you can try to solve today, and tomorrow you can come back. So what we observe is that this ALM is a frequency dependence. Okay. So the basically what I said is Planck. It measures map at different frequencies. So 30, 44, so in gigahertz, 70, 100, 143, 217, 353, 545, 857. Okay. Each one will have different beams. Okay, so the beams are not fixed. So it goes from 33 arc minute to 5 arc minute. So we don't need ALMs. So what we have is so assuming that we make them in a combine all the maps in a common resolution. So this is the original map. Okay, so we can make a common resolution map. So for this exercise, we assume that all the maps are say at 1 degree scale. Okay, 660 arc minute. Okay. So what we have is this temperature, delta T frequency. So it will have temperature of delta T CMB. Okay, it has a contribution of foreground and contribution of noise. Okay. So this frequency dependence is in the foreground and the noise. The CMB is frequency independent. Okay. Now our goal is to extract this CMB map from multi-frequency observation. So suppose we have this 9 frequency band. We want to extract this CMB. So individual each frequency. So this new can be 30 gigahertz. So you can write delta T 30 is equal to delta T CMB plus delta T F30 plus delta T N30. And like that, you can continue for different frequencies. So our goal is to measure what is the CMB contribution. So the CMB contribution can be obtained using very simple method called internal linear combination method. Combination method, which is ILC. So what it does is that it says, okay, I can extract a clean map by linearly combining all this delta T new map. Okay. So I have to sum over nu is equal to 1 to, in this case, 9 frequency maps. I have to just multiply by a weight factor, okay, which is W nu. But this weight factor we don't want the CMB to be get washed away or get biased result. So if we introduce a constraint that sum over nu, W nu equal to 1, okay. So in that case, this delta T clean, we can write it as, so this W sum over W nu is 1. So this delta T, okay, so let me write it down. We can write it as delta T CMB plus delta T F nu plus delta T N nu. So delta T CMB will come out because it's a common in all the maps, we can come out. So we get W sum over W nu. And the other ones, we will get W nu delta T F nu plus delta T N nu. Okay. So if we impose this condition, the sum over W nu is 1. So this becomes, sorry. So this is CMB. So we get delta T CMB plus some extra contribution. Okay. So you want to minimize this extra noise. Okay. So what should be the weight factor? Okay. So these are the weight factors. Okay. So what you have to do is you have to compute the variance of this delta T clean. Okay. So in simple notation, we can write it as W times the variance of the each map times W transpose. Okay. And the constraint is that W times E equal to 1. So you have to find from that what is W or what is W mu. So this weight factor is an array where is W1 W9. So you can take simple examples. So suppose you have two bands. Okay. So two frequencies. So you basically you have delta T1 map and delta T2 map. There are two maps. So we can always compute what is the variance. Okay. So the variance of this map we can call as 1, 1. And the variance of the second map is 1, 2. We can calculate what is the cross variance, which is 1, 2. So this is my variance map. Okay. Or the variance, it's not a map actually, it is variance of all the pixels. So what our goal is to measure delta T clean, which we write it as W1 times delta T1 plus W2 times delta T2. Okay. In such a way that when we combine like that, we will recover the CMB part, and whatever the foreground part, it is close to zero. Okay. So this bigger W that I'm writing is basically an column vector with W1 and W2, and this capital V, what I'm writing is two-dimensional matrix, which is V11, V12, V12, V22. So try to solve that and see what are the variants or the weights you are finding. I will share the notes of this lecture just after the class. Okay. So now we can okay. So you can hear me, right?
Yes.
Yes, sir.
Okay.
Yes, yes, sir.
Okay. So yeah, so now we can, so this is a basic thing. So it took me some time to go through it. So let me share my other screen and go through the so you can see my screen now, right?
Yes, you can see.
Okay. So what you can do is you can Google search Planck legacy archive. So if you want to work with the maps, it will go into this page. Okay. So if you have difficulty, you can write in the chat box. I will just go back and answer that. So then you can get a map section. Okay. So here you have all the data set. So there are many releases. Here only the legacy products are there. But if you unclick it and if you go back to any data set, okay. So it takes some time to load. So suppose PR1 I want to get. So this is, there are many data release of Planck. So the first one was 2013, and then we have 2015, 18, and the latest one was 2011. So here you can see there are these different frequency maps. So let me go to the legacy archive, legacy product. So this is the latest 2018 data set. So these are the different maps. Okay. So if you should, yeah. So if you just put into so let's see. Yes. So either you can download the maps. Okay, so this is what showing the maps in Aladdin. Otherwise, so we're going to use Hillpix to work with it. So we can either you can download it. I already download in the in my directory. So probably you can work with it. So these files are big, so you don't need everything to download. You can download one of the maps. Okay. So I suggest you download this 100 gigahertz NS 2048, or maybe 70 because it is smaller, 144 MB. So you can just download this file in your computer just for quick checks. Later on, from the group, you can access those other frequency maps. Okay. And this will show a small thumbnail which will tell how this maps looks like. Okay, so these are the full frequency maps, but suppose you want other maps, you can okay.
Sir, can we have the login ID and password?
No, this is Planck Legacy Archive. I think it is all publicly available. If you want to download, probably you can create a own username, password. So let's see.
This is free.
This is free. This is open. So yeah, if it is asking for this login and password, you can create your username and password. For downloading, you don't need any username and password. So I just now, like before the class, I download the files. I don't know why it is asking each time. So it is free. So this is publicly available data set. Okay. So it's asking me to sign in, but basically you don't need this. So here, basically all the maps are there. So after that, you are all registered into this Psi server. Did you create an account there?
Yes, sir.
Okay. So what you can do is you can let me do it. So if you click on, you have to create a container. So till now you have a tutorial session with the Psi server.
No, sir.
No, sir.
Sir, no, sir, no, sir. How you are doing this, sir? Please show us.
So you go to Psi server. So here basically you can share the data. So you have to create an account here. Okay. So once you create an account, I think this information was sent to all. So you can create.
Yes, sir. We have the accounts.
Okay, so I will just tell you after that how to do it. Okay, so if you log in, so I'm logging as Steve Ghosh, it will show this window. Okay, so I hope this you all can see, right?
Yes, sir.
Okay.
Yes, sir.
So then you go and click on this compute, which is analyze data and interactive Jupyter notebook in Python. Okay. So it will create, it will go to this page. Okay. So maybe it is,
Okay.
container is not there. You can create a container. Okay.
So
And
what is your container?
basically it is something from where you can open a terminal or Jupyter notebook. So if you
Okay,
have,
okay, yeah.
because you can work on your computer, but like downloading and everything takes some time. So if you, here everything is shared and is online, so you can just directly work here. Okay.
So do we need to select any of the public data volumes while creating the container?
No, no.
Okay.
Okay. So once it is container is there, you can click on this name. Okay. So it will open a Jupyter notebook. Okay. Something like that it will open. So here you can create a new Jupyter notebook. So here you can say, I want to create a Python notebook 3.8. So it will create a new notebook. Okay. So this is like, I think probably most of you are used to this Jupyter notebook for writing Python programs. And here you can do anything like 2 plus 2, it will tell you like 4. Okay. So
Hello?
this is, yes.
Yeah, is this computer service free? I mean, this Jupyter notebook, or
This
is it a subscription?
No, it's all free. So once you create that account, you can use that. And this Jupyter notebook is usually free. So if you want to install it in your computer, you can install it.
Okay.
So
Yeah, through an account.
everything we're talking about is free. So we are not, and nothing is paid. Hillpix is free. Jupyter notebook is free. So you can install in your computer. And otherwise, you can work it here in the site server. Yes. Yes.
So can you please show us that how we are going to create the container thing? And
I think it is create container,
no.
And you just give some name and just create, it should work. Just try. You can give some name here.
Yes, sir. Yes, sir. I'm trying.
Okay. So I think other tutorials are by Dheeraj and Suman. They are all in this site server. So you will get used to that. Okay. So it just, I'm also not very used to this. So it is like comes with practice. Okay. So, so the advantage is that you don't need to, yeah, it's working. Okay. So, yeah, so here you can give any name to your file. So suppose we are working with this software Hillpix. So you can give HillPy or Hillpix name. And
What it?
Yes. Yes, tell me. Hello. So this is basically HeatPix plus IPYNB. So this is a Python notebook. Okay. Now, so in the first page, it will show something which is shared. So I think you are all added to this workshop ISI group. Okay.
Yes, sir.
So if you click on it, it will show this workshop ISI. Okay. And then I have my name, Tuhin. So I put this to, because of the space limitation, I'm just putting this two maps. I think you can work. So for our purpose, because we want to learn it.
Sir.
Yes, yes.
Yeah, I can't see this workshop ISI thing. I only see the persistent and scratch folders.
Okay. So maybe you are not added to the group. So you can.
First you have to accept the invitation, then
yeah.
Otherwise you won't get.
Otherwise, otherwise what you can do is, for our purpose, we need only one map. So you can download the map, and like what I do is you can upload here, okay, in your directory. Okay. So so
Sir, you won't delete the files later, na?
Yeah, so like here, if you're in this group, you can always copy the file and move it to your home folder.
So if I copy their files to my directory, then if you delete this, then I will get the access even then.
No, this is in permanent, so I think it will not going to delete.
Okay, sir, thank
you. Yeah, so here they say there are two folders. One is storage and one is persistent. Okay. So in the storage, it is stored for long term. So they give you some space, and usually it is in this home folder, home IDs, workshop, storage, your username. Within that, it will be stored for long term. The other one is like temporary directory, where you store files for some time, and after some time they get deleted. Okay. So there are two options. Either you can download one image and upload there. Other is you can work in your computer also. Then we don't need this server. Yeah, but for other tutorials, you need this. So at least if you download and upload the files, you will get, you will know how it works.
Sir, how to copy the file from the directory to my working directory?
So that is a good question. So it is, yeah.
You need to click on this persistent.
Yeah, you can do copy from here and put in your home persistent directory and paste it there. Okay. So I'm just pasting it. So it will copy from this shared folder to your home directory. Okay. Double click it. Okay. So I think what the way it works is that this is a common directory created by Dr. Dhiraj. And so we are supposed to keep everything, but I think the space is running out here. So you can copy from this common directory to your home directory. So you can put in the persistent or scratch. So here my username is Ghosh. So you will see your username. So you can put it there. Okay. So they will be temporary, but at least the maps you can always download from Blank Legacy Archive. So it is not an issue. So what is needed is the code. And
Okay.
yeah, just 1 minute. So if you go to this on the top of this Jupyter, switch to Jupyter Lab, it will open. So you can open a terminal from that. So either you can, I think Jupyter Notebook is good, but just to let you know, you can work with the terminal also. So this is everything is online, and the data will be stored in this CI server. So your desktop space will not be used. Take some time. Okay. Yes. So it will show this kind of window. So here you can, in the storage or temporary directory, you can keep your the map files. Okay, so you can upload it from here also, upload files. So you can go to temporary and upload files. So you suppose you download the map, one fits file, and through this you can upload to your home directory. Otherwise you can copy from my home directory. And if you click on this terminal, it will open a terminal. So it is everything you can do it here. So I think the first step is to install the HillPy. So this HillPy, let me show you. So if you just type HillPy, so this is basically a Python version of HillPix, which is used to show to the maps. Okay, so there is an installation procedure. So if you're installing in this site server, so what you have to do is just type this command, pip install -- user HillPy. So in my thing, I think it is installed. But if you do pip install - user HillPy. Okay. So it will install in your home directory. Okay. So in my case, it is installed. You can just try. Let me make it bigger. Yes. So this is the command, pip install -- user HillPy. Okay. So did you all manage to install it?
Yes, sir.
Okay. So if you want to verify that whether it is installed properly or not, you do. Okay. It's becoming breaking down. So I need to. Okay. So you do IPython. So this is interactive Python, and if you just type import HillPy as HP. Okay. So if it passed through it and does not complain, then that means that the HillPy is installed properly in your system or in this in your home directory. Okay.
What is the
So
command?
how you get
Can
to
you
this
please-
green line by writing IPython?
IPython, yes.
What is the command, sir? Import HillPy as HP.
Yes.
Sir, I have a trivial question. Is there a reason we are not using Jupyter Notebook but Jupyter Lab?
No, we will going to use Jupyter Notebook just to
Okay.
verify that the HillPix is installed there or not.
Okay, okay, understood. Okay, thank you.
How did you enter Jupyter Lab?
Jupyter, so this is, okay, so first you have to create on this container, and then it will open this. You can create a new page, or you can use, yeah, so you can do a new notebook, and that is the Jupyter Notebook. So currently we are using the terminal to verify it.
How do you open the terminal, sir?
Terminal is you have this page, right? Jupyter. You
Yes, sir.
type on switch to Jupyter Lab, this window. Okay. So switch to Jupyter Lab.
Okay.
And then from that, it will open a terminal. So it is working. It will come. Yeah, and then if you type on this terminal, it will open this terminal or Jupyter Lab. Okay.
Okay, sir.
Okay. So in Python,
The command for
yes.
so the command for installing this HillPy is pip. Can you please show that one?
Yes. PIP install. I'm highlighting that. PIP
Yes, sir. Okay.
install -- user HillPy. We need only this much. We don't need anything else. Okay. So for anything, if you want to install any package, usually it is pip install, but usually it needs root permission. So if you do -- user, so then you don't need root permission. So in your home directory, it will install. Okay. So then you do in this window a question mark HP dot, and then you add tab. Yes. So it will show what are the different commands available in this HillPy package. Okay. So suppose one is anafast. So it tells you, if you just enter, it will tell you that what are the ingredients it needs. So this basically computes the power spectrum of Philpix map or the cross power spectrum if two maps are given. So if you give one map and you call as output, it will return the power spectrum. So like that, there are many commands. So each one you have to just type question mark HP dot, and then you have to type tab. So it will show what are the different options, and then with your mouse, you can go to any one or using the arrow key. Okay. So I'm just, so suppose I want to calculate given n site, what is the pixel resolution or like the theta I was discussing. So there is a code for doing that. So it's basically, it says that, so there is some description like what this code does, what are the input parameter, what is the output parameter, and how to call this, this routine. So like here it is, so you can just blindly copy paste. Okay. We will do it to Jupyter Notebook, but here we are just learning like how to use the HillPy. So if you do HP inside to resolution, and if inside is 256, if this is in radian, this is the pixel size. Okay. So this number is difficult to understand. So let's say we divide by multiply by 180 and divide by pi. So it means that 0.22 degree is the pixel size. Or if I do it in arc minute, I have to multiply by 60, which is 13.7 arc minute. So 256 resolution means pixel size in one dimension is 13.7 arc minute. Okay. So I hope you are able to install HillPy, able to open the Jupyter Notebook, and in the terminal you can verify that at least HillPy is installed. Okay. So let me stop sharing it. I'll give you the code. But I don't know where to. Yeah, so Hashwati Mandal, yeah, so you can try create your username in this Planck Legacy Archive to download the data. If it is asking, previously does not used to ask, but if it is asking, you can create a username, and so I think it is all free. I will check it again, and then you can download the data. Because I was not signing it, and I was able to download the data today's morning. So here, so in this chat box, let me see if I can upload the file on your computer. Just 1 minute. So I am just uploading a file, which is HillPy lecture day 1. Okay, so it is like 4 MB file, 4.96 MB. So you can download that Jupyter notebook in your computer. Okay, and then we can go step by step. Okay, so let me share again my screen. So if so you able to download the Python file, the Jupyter notebook.
Yes, sir.
Okay. Okay. So let me go through the Jupyter notebook, what is there, and tell you the steps so that you can practice. And tomorrow we can, if you have doubt, you can come back. Okay, so I will go through this Jupyter notebook and tell you like what are the different things here I do, so that you can practice today. Okay, and tomorrow, if it is possible, can we start at 2 o'clock instead of 2:30? So then it is okay with everyone.
Yeah, fine for me.
It's fine for me, sir.
Okay.
Yes, sir, no problem.
So we start at 2 o'clock. And because I have another meeting at 4 o'clock, so so we will at least 5 minutes before 4, depending on the lecture and the tutorial, we will cover. Okay. Okay. So so let me tell you how it works. So this is like you can do markdown. So if you want to write a comment, you can use markdown option. Okay.
So we have to open the notebook from this Jupyter file, then open like that. The notebook that we have downloaded.
Just copy paste it into this Jupyter here. You can just copy and paste it. It should work. So because HillPy is not installed in your computer, okay. So you can let me get rid of some of the windows because there are too many windows. Okay, so if Planck Legacy Archive, just try. If it does not work, you can just create a sign in, and then you can download the maps. Okay. Since I don't need it. HillPy, if you want to, I think they have some tutorial here. So if you want to practice like how the basic things works, it is in this HillPy tutorial page. Anyway, my thing is more elaborate, so you can go through my Jupyter notebook. Okay. So the idea is that you can copy from here. Okay, so you go copy and you put in this site server thing, paste, and it should work. Okay. And to enter, it is shift enter, shift enter or shift return. So this is a bit slow, but it will work. Okay. So let me go through the command so that you will know. So this HealPy is the package. Okay. And usually we, in Python, what we do is we import this package as some short name. So it can be anything. So we write it as HP so that we do $HP dot, it will show all the available options. And for plotting purpose, we need these two other package, NumPy and Matplotlib. So I think this is installed in Sci server. So you don't need to install this two other package. Okay. So this is just importing the libraries. Okay. And this plot.in is for interactive plotting so that it can plot in the same Jupyter notebook. Otherwise, usually it opens another window. This was in previous Python, but now I think this problem is resolved. So first step is to read the map. Okay. So suppose you download the map. So it has some name, okay, some name.fits. So for this purpose, any map should do. So from 30 to 857 gigahertz. So suppose you download one map, and then the command to read the map is this hp.readmap. So if you do in that Jupyter notebook, question mark, now it is not responding. Yeah, so maybe here. So if you do question mark hp.readup, it tells you how to read a map. So what we are doing here is we read a map and store into this variable M100. So just to identify that it is 100 gigahertz map. Okay. And then if I do what is np.shape, so it tells me what is the dimension of that array and how many pixels are there. So the Planck maps are generally, there is a high frequency maps and low frequency maps. So they are at NSIDE 2048. So NSIDE 2048 means the number of pixel is 12 times 2048 square. So it gives, this is something of this order. So that many pixels are there. So it's 50 million pixels are there. Okay. So this is the way to read the maps. And it tells you that what is the ordering of the map. So here it says that the ordering is nested. Okay. So what it does is
ordering in,
sorry, can you repeat it again?
Ordering means
yeah, your voice is cutting down. The ordering is like I said.
What is ordering?
I told you, no, there are two orderings. One is ring format and one is nested format. So ring is basically starting from North Pole and then it goes to the South Pole. And the nested is, it will try to identify pixels which are close to each other. Okay. So when you don't define anything, it will, it tells you what is the ordering of the input map. So it says that the ordering is nested. Okay. So either you can work with the nested map, or you can convert to ring format, and then we don't need, then it is easy to read the maps. It's just a convention, like how the pixels are defined. Okay. So if you want to, if you don't say anything, what it does, it reads the map and convert into ring format. It says that the original map is nested and this array is stored in ring format. If you want to keep this array in the nested format, you have to just add this keyword, that nest is equal to true. Okay, so then you want to keep this array in the nested format. Okay. And it has this header file which gives you the information about what is this file is, how many pixels are there, when this was observed. So this is all encoded in this header. So if you put h is equal to 2, header is equal to 2, and if you put a keyword header, so if you print header, it will give you all the information. So here what I'm printing is the header. It says that this all the information. So this file was created in 2017. So it says that basically from earlier we know that there are 3 columns in this. So the 3 columns are.
Sir, sorry to interrupt, sir. Sir, can you just send me the notebook link again in the chat box?
I think stop sharing, then I can do this. Okay. Yeah, send it now. Before me, Abhik Bhattacharya also sent again. Okay. So you can just.
I can't actually see the link. Where did you send it? In the chat box, right? In Zoom.
But in the chat box, nothing is showing, right?
Yes, sir. I guess you haven't sent it.
You have to, I think, send to everyone there
Yes,
in the chat box.
Okay. Oh, but I sent to everyone.
I've received it.
Okay. Maybe after. Oh, okay.
Can you actually upload the notebook to the folder inside server so that we can?
Yeah, that will be really helpful.
Yeah.
Let's see. Yes. I'm just doing it now. So I'm putting in this. Workshop ISI Tuhin, so it is uploading. So I uploaded it there in that workshop ISI. So let me share my screen again. Yes. So if you click on Tuhin, you will see this Python inode. Now you can see it in the shared folder.
Yes. Yes.
Okay. Okay. Yeah. So this basically has 3 indices, 3 columns. So one is the Stokes parameter I, type 1, and then we have Stokes U, and there should be Stokes Q. Okay. And all are in units of K CMB. Okay, so it's not in microkelvin CMB. Okay. And it says what is the N side, which is 2048, what is the frequency, and then there are other information. So most of them you don't need it, but it's just for if you want to know how this file was created, when it is created, what is in the header. There are some keywords inside that. Okay. So the first thing is, so we stored in the array, but we want to visualize whether like how this maps looks like. Okay. So there is a command hp.moleview. Okay. So if you just say that this is the array I want to visualize, but it array has 3 columns. Okay. So if you want to plot the first column, which is the temperature, you have to just put 0. The second column is your Q, third column is U. Okay, so then if you do just only this, it should work. But then there are other keywords like what is the color bar, what is the, how much is the, whether you want to show this color bar or not. Okay. What is the map format, whether it's nested or ring format, because I stored in a nested format. And so then you put it true, otherwise false, it is default. So if you, either you can write it nest is equal to false, or you don't write anything, which is same. Okay. Then you can define what is the minimum and maximum range. So this is all in Kelvin CMB. So this basically, usually the CMB maps we plot from minus 300 to plus 300. Okay, microkelvin. So in terms of Kelvin, it should be minus 3 to the power minus 4 to 3 times e to the power 4. And then we can put color title, so I map, which is or the temperature map, and the what is the color. So there is some default color bar for CM map in Python or matplotlib. So we can choose this color map. So it is just red and blue. Otherwise, it can it looks something slightly different color scale. Okay. So this is how we can visualize the maps. Okay. So this is I map. Then we can look at Q and U map. So you can see that in I, you can see something like CMB at 100 gigahertz, and then there are this galactic emission everywhere. Depending all the maps, any map you can choose and plot it, and you will see that it looks very different. Okay, so you can download those 7 or 9 maps and see like how this maps looks like. Okay. And so just to give you like what is the problem, if you assume that this map is in the nested format, okay, and if you don't write nest is equal to true, so the same array will look something like that. So it means that it's just a formatting error. So if by default, if you don't mention anything, so nest is equal to false, is assume that it is in ring format, then the same map which is shown here, okay, looks like this. So if you see this kind of stripes, it means that there is a problem. So either the map is in ring nested format, you are plotting in a ring format, or the input map is in ring format, you are plotting in a nested format. So this is way to identify whether there is a problem in the reading, because when we compute power spectrum, we need to give what is the exact ordering of the map. Otherwise, the power spectrum will not come out to be correct. So this is a like simple error if I just miss that point. So that's why it is always better to work with the ring format. Then you don't need to write anything about nest. Otherwise, you write nest. Suppose you start from a nest and always you write nest equal to true, nest equal to true, then it should work. Okay. So that is one.
Sir, M on 0 0. Then beside it you put 0 in third bracket. Why, sir? Why 0?
So 0 is means first column. Okay. So this okay. So I have this M100. Okay. So I have I know there are 3 dimensions, 3 columns, and I have some 50 million pixels. Okay. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. No. Okay. So this pixel number we are not interested. So we can do like this. Okay. So this is the dimension of the M100. So if I put 0 here, it means that this is, I'm reading the temperature map. Okay. And the shorthand notation is, I don't need to, even to put this semicolon. I can just write M100 0. So this is same as M100 0, comma this. Then if I want to write 1, comma this means Stokes Q map. Okay. So this is M100. I can write it 1. And so I have 3 columns only. So I can do 2, comma, star, which is Stokes U map, which is M100. Okay. Okay. So these maps are usually used in galactic coordinate system. So basically this is like a galactic center, and from the galactic center we are looking up or down. But then there are other coordinate system used by astronomers. So this is ecliptic coordinate system. So this is something with respect to galaxies, it's not with respect to us. Okay. So this ecliptic system is something which is convenient for to see which portion of the sky we can observe from a given location. So this is ecliptic coordinate system. So we can always change the coordinate from galaxy to ecliptic, okay, depending on your need. So for us, we don't need it, but it's just to give you an idea that if I want to visualize the same map instead of galactic coordinate system, if I do it in ecliptic coordinate system, it looks like this. So this map is same as this. Okay, it's just I choose different coordinate system to define this map. So the advantage of this is that suppose we are say in Kolkata, okay, we set up a telescope, we can only observe this northern hemisphere. Okay, so we'll not have access up to some declination we can measure. Below that we cannot measure it. Okay, so the Planck is a space mission, so it can observe the full sky, but from the ground, if it is northern hemisphere, we can observe this like at least some 60 or 70% of the sky from the northern hemisphere, and from the southern hemisphere we can observe this like from the south another 60 to 70% of the sky. Okay. So this BICEP experiment, they look at this southern galactic cap region. So this is somewhere here. Okay. When we do coordinate transformation, it is something here. So it is very weird. It's just a changing the coordinate system. Okay. So something which is important to note, like what part of the sky we can cover, which is the RA and the declination. Okay. So the next thing is, so we have these Planck maps. So they are a different resolution. So in some purpose, it is good to have the maps at the common resolution and then compare it. Then we will know that what is like how different they are. If they are a different resolution, it is hard to compare. Like if you compare Kobe and Planck, so Kobe did not look at the small scales, Planck looked at it. So it is hard to compare whether these two experiments are consistent or not. So if you, what we can do is we can always go back to low resolution map from high resolution map by smoothing. Okay. So it is like the beam is Gaussian. So this 100 gigahertz map has a beam of around 10 arc minute. Okay. So if you want to smooth the map to say 5 degree, you have to do this FWHM. So what is basically, suppose there is a beam which is sigma 1 and another beam is sigma 2. Okay, so if you want to go from sigma 1 to sigma 2, so the extra smoothing you have to apply is square root of sigma 2 square minus sigma 1 square. So when you smooth it, this is how it looks like. So this map, these two maps are one is unsmooth version of the real data, other is thus with applying smoothing. So this is to basically cancel out the effect of the noise and to highlight the structures. Okay. Another thing what we can do is to downgrade. Okay, so we can choose original map is 2048. So we can always downgrade or upgrade the maps. Okay, so upgrade does not make sense, but the downgrade, we can make it low resolution map. So it's all factor of 2 to the power n. So we can downgrade to n side 64. Okay, or 126. So whatever number, 128, whatever number you want to select, you can downgrade the maps and look at like what is the effect of smoothing and the pixel resolution. Okay, so this is all full sky map. Okay, so this is called as mole wide projection, but we can look at some particular sky region. So like suppose I want to zoom on this region and I want to see how it looks like. Okay, because in the total thing, suppose I'm not interested in, and I want to interested what is going on in this sky region. So then there is a command called hp.genomeView, which basically what it does, you take the map, you say what is the coordinate system around which you want that you want to see what is going on there. So this LMC is a large Magellanic cloud. So this is a small galaxy, satellite galaxy of Milky Way. So we can visualize this using this command. So I think I will stop here. So the idea is that you get used to Sci server, try to open the terminal Jupyter notebook. Okay, try to transfer this 7 or 9 maps into your home directory. Okay, and you just go through this first part of this thing, how to visualize the maps, and full map. And
after smoothing, why it is get so much?
After smoothing,
why it is get so much blood outside?
Blurred outside, yes. Yeah, so because when we smooth, okay. So when we smooth, it's not that we are reducing the noise, we are reducing the signal also. So the CMB power spectrum has a shape, right? So what we are doing is multiplying by BL. So it wash out that relevant scales. So this is mostly coming from the small scale features. So now say there are red, blue, these patterns are there. So when I am averaging over bigger beam, what I'm doing is I take an average over this remaining number of pixel and allocate a central value. And then I go to the next pixel, I average over big region. Now here regions are dominated by blue, some regions are dominated by red. If I average it, the amplitude becomes smaller. So it wash out the signal also. So smoothing is not it is way to enhance the signal, but the signal is also there on those scales. So we just wash out the signal. That's why it is not, so here it is 300 to plus 300 because they are blue and red. But here, when I plot from 300 to 300, it is not that dark blue. So it is light blue. So it is something like 100 microkelvin. Okay. Yeah, and one last part. So these files are not there. That's why it complained. But if you download the relevant files, it should work. Okay. If something is not working, you can just remove those lines. The last thing which is important is to compute the power spectrum. So suppose you start with one map, and if you want to compute what is the power spectrum, so only doing this command will be enough. So if you do hp.nfast of the map, so here should be 0 because I have 3 arrays. Okay, so for temperature, I do, and then I choose Lmax. So Lmax is generally 2 times n side. So the n side is 4096, N max, N side is 2048. So if you choose 4096, okay, it will calculate the CL and stored in this file. And then if you do this, this simple command, plot log L times L into L plus 1 CL divided by 2 pi, it will plot it. And then this is just to convert from Kelvin CMB to micro Kelvin CMB. Okay. So you take these maps and just compute the power spectrum using this command and see how this power spectrum looks like. Okay. So you can try without smoothing, with smoothing, and see what is the how it looks like. Okay. So these notes are there. So I will send you like the initial part of the note now. Like what is maybe you all have access to the Slack, right?
Yes, sir.
Sir, please upload your note also to CIHISI.
Yeah, okay, okay. I will do that. I will upload in the Sky server. Okay.
Hello.
Yes.
Can you repeat how to install a HILPI?
Yes. So you do pip install pip space install. Write it down. So what you do is pip install minus user HILPI.
Hello, sir. I have a few questions. So first question is that so when we plot this CL now, so this will be containing foregrounds as well. So this will not be the correct CL that we want. So we have to remove the foregrounds first, right?
Yes.
Okay. So the second part is, so what is the benefit of smoothing if it is also removing the actual signal?
No, suppose, so I don't have. So this CMB power spectrum, okay. So like yesterday I was showing the plot. So it peaks around 200.
Okay. Right, yeah.
Now, if you want to smooth only the very large L, so up to say after say 1200, L is equal to 1200,
Yes.
you want to reduce the noise. Okay, so there the signal is washed out, but the signal is not much contribution there after 1200, say. Okay, so then you can apply smoothing. What I'm here doing is 5-degree smoothing. Okay, so that's why it is peaking. So when I do, let's see. So this 5, so you have to convert into radians. So here I'm doing 5-degree smoothing. So when I'm doing 5-degree smoothing, it is washing out the peak because the peak is at 1 degree. I'm doing 5-degree smoothing. But in principle, from 10 arc minute, you don't need to do 5 degrees. So suppose you go from 10 arc minute to say 20 arc minute.
Okay.
So then it retains all the shape, signal, most of the signal. It reduces some part of the signal or like wash out the signal, and most of the noise, it gets washed out. So it is to increase the signal to noise.
Yes. So there should be a way, like we are cleaning the foregrounds to clean, like separate this noise as well from the signal.
Yes.
Yeah. Okay. So another thing. Sorry, you can.
Yeah, you continue.
Yeah. So another thing that is not from HILPIC. So in the earlier part of your lecture, you mentioned that EB cross correlation will be 0 if there are they are actually 0, but the instrumental noise can make them non-zero, right?
Yes.
But sir, like these are non-zero as well as for this lensing potential. Like when we use the lensing potential estimator, we use the EB cross correlations. So there we have non-zero EB cross correlation
No,
as
for,
well?
no. For lensing, there is a E leaks into B.
Yes.
But if you are computing the EB power spectrum, so there we are, because it leaks into B, so there we are computing the BB power spectrum or EE power spectrum. Okay. We are not computing EB power spectrum.
Actually, I will check, but for some of my this exercises, I have calculated the EB cross correlation as well. But that's true that their power from the E was leaking to the B. That was the case, but the EB correlation was not 0.
Yes. No, I think for CMB, EB should be 0.
Okay, I'll check, and if I find the case, I'll email you, right?
Yes, sure.
Yeah.
So, yes.
Sir, show us the power spectrum value in this code calculator.
What is the power spectrum value?
Yes.
No, so you take any map, it does not matter. This will compute the power spectrum of that. Okay.
We don't need to define the angle 5 minutes or 15 minutes like that.
So this is CL. So what I'm telling you, and this CL is start from L is equal to 0 to L is equal to 4096. Okay. So you have to define what is L. So np.a range, it is just assigning that it is 0, is an array of dimensions, say 4096. Okay. And it is just a dimension like 0, 1, 2, 3, 4, and then you just plot L times L by L and L plus 1 CL by 2 pi. Okay. You don't need any more information. It is just for each L, it is computing what is the CL.
What is this text file? Discom power spec CMBTT.
Yeah. So this is the best fit lambda CDM model. Okay. So that file is also there in this Psi server. So if you want to plot what is the best fit lambda CDM model. Okay. So then you can just plot L best fit and DL best fit. So this is usually in DL. So it is already multiplied by all this L into L plus 1 CL divided by 2 pi. So that's why you don't need to multiply again. So there is 2 conventions. So if you're taking from the map, it is always CL, and then you have to multiply by L into L plus 1 CL divided by 2 pi. And in model thing, sometimes they are all constructed in a DL format, which is this L into L plus 1 multiplied already. So then you don't need to multiply. So this is just for reference. You can just plot this and see how much each frequency map deviate. What is the power spectrum? How much it deviates from the best fit lambda CDM model? Because here we're not subtracting any foreground or noise or anything. So, and there are beams and other things. So you will see like what is like how the power spectrum derived from any map, how it compares with the lambda CDM model. Okay. So then you know that, okay, given frequency maps, I get this power spectrum. And this is a good exercise you can do today, and tomorrow you can show me. This is what the power spectrum looks like for different frequency maps. You can do it with one, or you can do it randomly, all the 6, 7. It's just putting in a loop. Okay. And this is my best fit lambda CDM model. So now the goal is to go from this model. Currently, this data set we have to the lambda CDM model, because we know that universe is lambda CDM, dark energy, dark matter, baryons, all these things are there. How to go from this real sky map to something which is lambda CDM. Okay.
So where should we put the new?
Thank you.
So where should we put the new feeds files, the new frequency ones that we want to use? Because I tried to use the 30 gigahertz one, but
yes,
it is saying that file is not found.
You can download from PLA, Blank Legacy Archive, because I think...
no, sir, that one you have already shared in the Psi server.
Okay.
So I tried to do that, changing the file name there, but it's saying that the file is not found.
you have to just do, or you can just download, because this is 144 MB file. Okay, I will try to download, because what I understand is this, I think this shared space is limited. So even if I download it and share in the Slack, it is not going to help, because, okay, so. I was thinking like, what is the best way to transfer the maps to you?
So you have actually uploaded the 144 MB file, that the sky map of 30 gigahertz, that is already there in the folder.
So then it should work.
Yeah, so, but when I change the file name, that one is given LFI sky map 30. So it is saying that the file is not found. So do you have to put a path or something like that?
No, you have to just copy, and you go to this directory. You have to just copy.
Okay.
And you go to your home directory.
Yeah.
So here you will be owner. So say in the Scratch directory, you just paste. So it will paste in your home directory. Okay. Now you open a terminal and you go to this temporary space directory. So it will be /temporary/ your username /scratch. That file will be there. So let me try. So if I go here, I will go to Jupyter Lab. So first thing is to find the location. So if you know the location, then in the Jupyter notebook, you will give the total path. Then it will work. So you go to terminal. Okay. So this is my terminal. So you go to workspace, temporary.
Okay.
And then Ghosh, Scratch. So I have this file. So this is the path. Okay. So in that, before giving the file name, you give the whole name. So you will copy.
Okay.
And you do it here, say like this, path, and then in the file name, it should work.
Okay. Okay. Thank you, sir.
Sir.
Yes.
Yeah, this CL has, I think, 6 columns. So which column do we need for the plotting?
Yeah, first one.
Okay, so 0th column, right?
0th column, yes. So 0 is my TT power spectrum. The way it is arranged is TT, then TE, then TB, then EE, then EB, and BB. So there are, so if you read TIHISI documentation, okay. So there are 2, so this was the older one. New one is something like TT, EE, BB, TE, TB, EB. So this is new scheme. And this was old scheme. So you can switch from one to another. Okay. So there is a, so let's see. So TIHISI. Yeah, so this is the new one, the way it is written. So it gives you TT, EE, BB, TE, EB, TB. So first one, 0 if you put, you get TT. If you put 1, you get E power spectrum, and 2, BB. So E and B polarization is details. So we can work with the first temperature and get an idea that how to visualize things. Okay. Anything else?
Okay, sir. Thank you.
Okay. And you try to do the exercise that I gave you, like what is the weight factors. And then tomorrow we will need that. So tomorrow we'll start at 2 o'clock. So there will be first we have the lecture, and then the second part, second half, we will do this hand-on session. Okay.
Okay, sir. Thank you for the nice